Hello students, in the last class we have completed the overall study about the 17 group elements, as well as we have seen some of the important preparations, along with that some of the uses as well as structures of the molecules also we have studied. That is oxo acids of halogens like chlorines, so that also we have studied. And the last part of this concept or this chapter is that is group 18, and today we'll finish with the group 18 elements, and this is the last group in case of a periodic table, that is which is generally present in case of p block elements. And group 18 elements are generally called as noble gases also. The another name for group 18 elements is generally called as noble gases, and these are helium, neon, argon, krypton, xenon as well as radon. There are 6 noble gases in case of p block elements, which means overall in case of periodic table. So these are considered, or these are categorized under the 18th group or group 18 elements, which are also known as noble gases. Here if you see, again I have made a 4 column here for the clear understanding. One is element, second one is atomic number, third one is atomic mass, and fourth one is its respective electronic configuration. Here if you observe, the helium is the first element in group 18, and atomic number is 2, atomic mass is 4, electronic configuration is 1s2. And neon, the atomic number is 10, atomic mass is 20.18, and the electronic configuration is the nearest noble gas is helium, that is 2s2, 2p6. And next element is argon. There is a third element in the 18th group. So, and atomic number is 18, atomic mass is 39.95, and the nearest noble gas, if I write the electronic configuration, that is neon, 3s2, 3p6. Similarly for krypton, it is 36 atomic number, atomic mass is 83.80, and electronic configuration is argon, 3d10, 4s2, 4p6. Similarly xenon is the fifth noble gas, and its atomic number is 54, its atomic mass is 131, and electronic configuration, nearest noble gas is krypton, and it's 4d10, 5s2 and 5p6. And the last element of the group 18, that is radon, and it is having the atomic number of 86 as well as the atomic mass of 222. And if you go through the electronic configuration, the nearest noble gas is xenon, and it is 4f14, 5d10, 6s2 and 6p6. And all these noble gases are highly unreactive. Remember, these are not reactive, these are generally called as unreactive, right? Further I will tell why these are unreactive. And the most important thing you have to observe here is, if you take the electronic configuration of all the the noble gases except helium, that is the first element of the 18th group. So other than that, all other elements like neon, argon, krypton, xenon as well as radon having the outermost electronic configuration, that is general electronic configuration, is ns2 np6. The general electronic configuration except the first element of the 18th group, that is helium, all other elements have the electronic configuration of ns2 np6. So since these are completely filled, right? So s orbital consists of maximum 2 electrons as well as p orbital consists of maximum 6 electrons. So therefore all the orbitals are here completely filled. For example, if you take here, this is a p orbital which consists of 3 p orbitals, px, py and pz, and this is one s, this is px, this is py and pz, right? So therefore in s orbital maximum we can fix 2 electrons, right? So here it is 2 electrons, and here it is px, py and pz also completely consist of the electrons. So therefore it is in the configuration of ns2 and np6. Therefore it is ns2, s orbital is completely filled. Similarly p orbital is also completely filled, np6. So therefore due to the complete filling of all the orbitals, or so due to the complete filling of these orbitals, generally these are unreactive in nature. Generally these are unreactive or non-reactive in nature. Remember, so the general electronic configuration, that is outermost except helium. This is very important, except helium, because it is 1s2. So other than helium, all the other noble gases, all the other 5 noble gases like neon, argon, krypton, xenon as well as radon having the outermost electronic configuration of ns2 to np6. And atomic and ionic radii increases down the group as you come down the group from helium to neon, right? So what happens, the atomic as well as ionic radii goes on increases, which means helium has very lower size, so that the atomic radius is very less, and it goes on increases from helium to neon, neon to argon, argon to krypton, like this, from helium to radon as you come down the group. If you come down the group here, so in this way what happens, there is an increase in the atomic as well as ionic radii down the group. And due to stable electronic configuration, these exhibit very high ionization enthalpy. right? So as I said, so these are completely filled, right? So outermost electronic configuration, if you observe here, so it's having the completely filled electronic configuration. Here if you observe, it has completely filled electronic configuration. So therefore, to remove the electron from this orbitals, any of the orbitals, is not so easy, because one is having the attractive, both are in opposite direction, they will have the attractive force, more attractive force. So therefore, the another electron will not leave its own electron, right? So one of the electron from that orbit. So therefore it is highly impossible, or you need high amount of energy to remove or to break this whatever the attractive force is present between the two electrons. So therefore, you need more amount of energy to ionize or to remove the electron from the last orbit. Therefore, due to stable electronic configuration, remember, due to stable electronic configuration, so these 18 group elements are generally having high ionization enthalpy, right? So these are the 4 to 5 important general properties of group 18 elements. Once again, I will say, so there are 6 noble gases which are present in terms of group 18 elements. So those are helium, neon, argon, krypton, xenon, as well as radon, and these are also known as noble gases. And the outermost electronic configuration other than helium, all are having, that is ns2 np6, remember that one. And due to the complete filling of orbitals, these have very high ionization enthalpy. And further, if you go for the physical properties of group 18 elements, all these noble gases are monoatomic. Remember, they are not diatomic. All these mono gases are present generally in terms of monoatom. Mono means single, right? So monoatomic form, and they are colorless, odorless, and tasteless. Remember, these are colorless, odorless, and tasteless, and they are sparingly soluble in water. They will not easily dissolve in water, or they will not easily mix with water molecule. So therefore, these are generally termed or considered as sparingly soluble in water, not completely soluble, or not more extent, the solubility will not be observed for the more or greater extent. So therefore, these are generally called as sparingly soluble in case of water molecule, and generally they have very low melting as well as boiling point, since the reactivity is very less. Along with that, the completely filled electronic configuration also, that is also one of the important physical property. And along with that, these 18 group elements or noble gases are generally having low melting as well as boiling points. So as I've already mentioned, the noble gases except helium, that is 1s2 electronic configuration, so all have the completely filled ns2 np6 electronic configuration in the valence shell. So as we said, in case of general properties, so the noble gases except helium, other than helium, because it is 1s2, as we've seen in the electron configuration, that is stable. So here, other than helium, all the other elements like neon, argon, krypton, xenon, as well as radon are having the outermost or the valence shell electronic configuration, that is ns2 and np6. And as we said, the high ionization enthalpy and more positive electron gain enthalpy can seen in case of group 18 elements. So these are the some of the physical features, like physical properties as well as general properties in case of group 18 elements. So in this group 18 elements, for your syllabus, there is no any kind of chemical reactions or chemical reactivity, which means chemical properties. Directly there are some of the important preparations, which means the bonding, how the bonding can take place, or how the compounds can be formed. In that, first one is xenon of fluorine compounds, right? So first one is xenon fluorine compounds, and second one is xenon oxygen compounds, right? So we'll go through the first one, that is xenon fluorine compounds. Generally, xenon forms 3 binary fluorides. Whenever it reacts with fluorine, that is xenon. Xenon, whenever reacts with fluorine, it converts into 3 binary fluorides. Remember, 3 binary. Binary means 2, right? So binary fluorides, which means it is bonded with, it is made up of 2 elements. One is xenon, another one is fluorine. So xenon, when forms 3 binary fluorides, these are in the form of XeF2, XeF4, and XeF6. Remember, it is in the form of xenon difluoride, tetrafluoride, and hexafluoride. Remember, it can be in the form of xenon difluoride, right? So, and it can be the form of, whenever it bonds with a 2 fluorine atom, it will be difluoride. Whenever it bonds or reacts with 4 fluorine atom, we will call it as a tetrafluoride. So that is 4 fluorine atoms are bonded with the xenon, and it may be in the form of hexafluoride also. Whenever it bonds with 6 fluorine atoms, we will call it as xenon hexafluoride. It's very simple reactions. Whenever xenon reacts with 2 fluorine atoms, remember, at the temperature range of 673 Kelvin and very less pressure of 1 bar pressure, and that will convert into xenon difluoride. There is addition of 2 fluorine atoms, it will convert into xenon difluoride. Whenever this xenon bonds with or reacts with 2 moles of F2, which means that is 4 moles. Generally, it is 4 moles. That is 2 moles of F2, and it will convert into xenon tetrafluoride at the temperature range of 873 Kelvin and the pressure of 7 bar pressure, right? So at 7 bar pressure, it will convert into xenon tetrafluoride. When it bonds with fluorine atoms, we'll call it as tetrafluoride. And the same reaction, if you increase the concentration of F2, that is, if you take 3 moles of F2, so it will generally convert into hexafluoride. Therefore, xenon forms a 3 binary fluorides whenever it reacts with the fluorine. Those are in the form of XeF2, that is a difluoride, XeF4, tetrafluoride, XeF6, that is hexafluoride. Right? A xenon difluoride, tetrafluoride, and hexafluoride are generally colorless crystalline solids. Remember, all the three are colorless, and these are generally crystalline solids, and they are powerful fluorinating agent, right? So fluorinating agent means in the addition of fluorine to any of the organic compounds or inorganic compounds, right? So as we said, in case of alcohols, some of the reactions we have seen hallucination reaction. So in that fluorination, like that, you can use these compounds like xenon hexafluoride, xenon tetrafluoride, which are rich with fluorine, has the ability to give fluorine ions for bonding with it. They are given organic or inorganic compounds. So therefore, they are very powerful fluorinating agents. And the next thing is xenon oxygen compounds. So these xenon oxygen compounds are obtained by the hydrolysis of xenon fluoride and xenon fluoride, generally xenon tetrafluoride and hexafluoride. Once you prepare this xenon tetrafluoride or xenon hexafluoride, so with that hydrolysis means addition of water, right? So addition of water, so you can prepare the xenon oxygen compounds. If you have already prepared this xenon fluorine compounds, along with that xenon fluorine compounds, so by adding water molecule for that, which means generally we call it as hydrolysis. Hydrolysis means process of addition of water molecule, right? So due to the process of addition of water molecule, you can get, right? So water molecule generally consists of H2. This all oxygen molecule can be bonded with the xenon. This oxygen molecule can be bonded with the xenon. So therefore, it can convert into xenon oxygen compound, right? So very simple. So we have already studied the preparation of xenon fluorine compounds. Once you prepare xenon fluorine, it is direct method. When xenon reacts with fluorine, it will convert into xenon difluoride. If you increase concentration, it will become tetrachloride. If you increase the concentration of fluorine again, it can be converted into xenon hexafluoride. So therefore, further, if you can use the same xenon fluorides for the preparation of xenon oxo compounds or xenon oxygen compounds only just by the addition of water, and this process is generally called as hydrolysis. The hydrolysis of xenon tetrafluoride or xenon hexafluoride with water molecule gives xenon trioxide. Here if you observe, that is XeO3. Right? So here it is very simple. Xenon hexafluoride, when reacts with 3 moles of water molecule, there will be a removal of fluorine and the addition of oxygen. There is a removal of fluorine and addition of oxygen. It's look like a displacement reaction, which means here the fluorine is displaced or replaced with the help of oxygen due to the addition of water molecule. Since we are adding water molecule, this process is called hydrolysis. Very simple. Once again, I will explain. Whenever you take the xenon tetrafluoride or xenon hexafluoride, and if you react with water, that process is generally called as hydrolysis. During hydrolysis, what happens? So the oxygen has capability to replace or displace this fluorine atom which is already present with xenon. So therefore, this oxygen takes the place of fluorine, and this fluorine will comes out along with this hydrogen. So therefore, further it will convert into hydrogen fluoride. That is a side product. The main product which is required is xenon oxygen compound, that is xenon trioxide. Xenon trioxide, very simple. And partial hydrolysis, this is a complete hydrolysis. And if you go for the partial, which means it is incomplete, which means the partial hydrolysis of xenon hexafluoride gives oxyfluorides. So generally they convert into oxyfluorides, which are in the form of XeOF4, XeO2F2, which may be in the form of XeOF4 and XeO2F2. Right? So if XeF6, that is xenon hexafluoride, reacts with water molecule at a partial hydrolysis, right? So it looks like the same process, but here it is partial hydrolysis. No, there is no any kind of complete hydrolysis. So due to partial hydrolysis, what happens? It will convert into xenon, that is oxyfluorides. Generally, they convert into xenon oxyfluorides along with the liberation of hydrogen fluoride. Similarly, xenon hexafluoride, when reacts with 2 moles of H2O, it can convert into XeO2F2 along with the liberation of 4HF. Right? So this is the important preparations for xenon oxygen compounds. And if we go here further, here xenon tetraoxide is colorless explosive solid, which means which has capability to explode right? So, and this is very explosive solid and has a pyramidal molecular structure. If you see the structure of this molecule XeO3, generally it is in the form of pyramidal. Generally, it is in the form of pyramidal structure, right? So, generally, you have studied in case of VBT, valence bond theory, and VSCPR theory, right? So, molecular orbital theory. So, different theories helps to predict the structure of the molecule that you have already learned in first PUC. So, here, further in coordination compound also, you study the structure of molecules. Just remember, xenon trioxide is generally having the pyramidal molecular structure, so which has the quality or capacity to explode. Generally, it is called as explosive solid. And if you go for a xenon oxyfluorides like XeOF4, if you go for XeOF4, it is also colorless and it is a volatile liquid, which means it is easily evaporates. It easily evaporates. Generally, we'll call it as volatile in nature. So XeOF4 is colorless and it is volatile in nature and has a square pyramidal molecular structure. So XeO3 is generally having pyramidal molecular structure. XeOF4 is generally having the square pyramidal structure, right? So this kind of questions may be asked in CET, right? So they will give the molecule and they will tell to predict the type of bonding or predict the type of structure of the molecule, right? So whatever the structure, they will give 4 options and they may ask. Otherwise, they will give the structure of the molecule and identify the molecular formula of that particular substance which is having this kind of pyramidal molecular structure or square pyramidal molecular structure. Just remember, xenon trioxide is generally having the pyramidal molecular structure, and xenon oxofluoride, so which is XeOF4, is generally having the square pyramidal structure. And further, if you go for the structure of xenon compounds, that is XeF2. So if you go for the further the structure of XeF2, so here the xenon is having a 3 lone pair of electrons. Here if you observe, this is 1, 2 and 3, and in the other side it is bonded with the fluorine atom with a single bond. That is the linear structure. And the square planar structure of xenon is bonded with 4 fluorine atoms and it is having the 1 lone pair of electrons generally. So here if you observe, the xenon is bonded with the 4 fluorine atoms and which looks like a square, and it is a planar structure, that is on the plane, so therefore it is called as a square planar. Here if you observe, xenon is bonded with 4 fluorine atom and 1 lone pair of electron. This is generally called as square planar. Whenever it is in the linear structure, xenon is bonded to 2 fluorine atom, that is XeF2, right? So this is the molecule of XeF2, right? And this is the molecule of XeF4, right? So whenever it is in the form of XeF4, what happens? It can be in the form of 4 single bonded with fluorine atoms, so 1 is lone pair of electron. But in case of linear, what happens generally? So here xenon is bonded with the 2 fluorine atoms which are single bonded, and further there are 3 unpaired electrons, right? And if you go through the structures of xenons when they react with fluorine, there is another one when it reacts with the 6 fluorine atom, that is XeF6. If you go for XeF6 molecule, so it is having generally 6 fluorine bonds along with 1 lone pair of electrons, right? So generally xenon is having 6 fluorine, that is single bonded molecules, and further it is having 1 lone pair of electron. You can observe here, right? So 1, 2, 3, 4, 5, 6. 6 are single bonded, that is covalent bonded xenon with the fluorine, and it is having 1 lone pair of electron. That is the structure of XeF6. And if you go for the xenon oxyfluorides, so in case of oxyfluorides, if you see here, that is XeOF4. XeOF4. Here you can observe the xenon, right? So the xenon, which is a single bonded with the 4 fluorine atoms, and it is double bonded with 1 oxygen. It is double bonded with 1 oxygen, and there is 1 lone pair of electron, which is generally in the square pyramidal structure, as we already seen xenon XeOF4, right? So this molecule XeOF4, so is generally having the square pyramidal structure that we have already seen. Here the xenon is single bonded with the 4 fluorine atoms and double bonded with the 1 oxygen, and there is 1 lone pair of electron in case of XeOF4. And if you further go for the xenon, which is bonded with 3 oxygen, that is XeO3, xenon trioxide. If you go for xenon trioxide, so in that what happens? Generally xenon is bonded with 3 oxygens with a double bonded. Generally it is bonded with 3 oxygen with a double bonded, and there is 1 lone pair of electron in case of XeO3. That is generally called as a pyramidal structure that we have already seen previously. So XeO3, that is xenon trioxide, is having the pyramidal structure, and xenon oxofluoride, that is in the form of XeOF4, is generally having the square pyramidal structure. That is Xe bonded with the 4 fluorine atoms, and 1 is double bonded with oxygen, and there is 1 lone pair of electron, which can be seen in case of XeOF4, right? So these are the some of the important structures of xenons, and this is asked for 1 mark. Most of the time they have asked for your annual examination. Go through the old question paper, you will see the question that is XeF4 is the most time repeated question for the annual examination for 1 mark. Further, if you go for the uses of this xenon compounds or 18th group elements, generally helium is non-inflammable. Generally, it is non-inflammable, and light gas. It is helped in the uses of balloons, like in case of birthday parties or in case of any special kind of occasions, right? So for filling the balloons, or in case of the parachutes, whatever issue which are in the kind of the balloons, right? So in that we can use the helium gas, because helium is very light gas, so therefore it is and it is a non-inflammable also, right? So there is no any chance of catching fire, so therefore it is generally used in case of filling the balloons. Different colored balloons can be filled with the help of helium, so and these are light and it can float above the surface of earth also, right? And it is used in the gas cooled nuclear reactors, right? So in case of nuclear reactors, so the gas cooled nuclear reactors, the helium is used, right? And it is used in the production of magnets. Generally the helium or either kinds of the 18th group elements, which are known as noble gases, are used in the production of magnets, right? For the essential parts of nuclear magnetic resonance, that is NMR spectroscopy, and MRI, that is magnetic resonance imaging, in case of whatever they will use for taking the MIR, that is scans imaging, that is magnetic resonance imaging, in body scanning also, and which is generally used in hospitals, so for the study of body. So in that cases, for the production of those machines, generally for the making of the magnets, which can be used in case of NMR as well as the MRI, right? So those machines, so we use the magnets. For the production of those magnets, the noble gases or group 18 elements are generally used. And neon is used in the discharge tubes and fluorescent bulbs, right? So in case of bulbs, so the different kinds of bulbs now we can see. So along with that, these are some of the important bulbs in case of discharge tubes, like fluorescent bulbs also we can use the neon gas, right? So whenever you break that bulbs or tube lights, so there will be a huge explosive like sound. So that is mainly due to the presence of neon which is present in that. And neon bulbs are used in the botanical gardens and greenhouses. So generally these are used in case of botanical gardens as well as the greenhouse gases also. Greenhouses also we can use the neon bulbs. So there are some of the scientific reasons for the uses of this neon bulbs in case of botanical gardens as well as in case of greenhouses also, right? So these are the some of the uses of group 18 elements, and these, which are also known as generally the noble gases, right? So that is all the information about the group 18 elements. It is very less for your syllabus, and once we'll see what we have learned today. Okay, here if you observe in case of group 18 elements, as we said that there are 6 noble gases which are present in the group 18, or which are categorized in group 18, that is helium, neon, argon, krypton, xenon and radon. The most important part is you have to remember the outermost electronic configuration. So it is NS2 NP6, that's why they are present in case of group 18, or they are grouped under group 18. And all the physical properties also we have seen. Along with that, the important general properties also we have seen, and along with that we have seen some of the important molecules or the preparation of compounds like xenon fluorine compounds, or you can also call it as xenon oxygen compounds. Though very simple preparations. So whenever they react with fluorine, they can convert into 3 binary fluorides. One is difluoride, tetrafluoride as well as hexafluoride. So along with that, we can prepare the xenon oxygen compounds. By using the xenon fluorine compounds, we can also prepare the xenon oxygen. And in the last part also we have seen some of the important structures in which xenon tetrafluoride is most important. It has repeated for your annual examination. Be careful with that question. And at last we have seen some of the important uses of the P block, that is 18th group. Generally, specifically you can call it as 18th group, or which are also known as noble gases, right? So this completes the overall chapter, that is P block. So in the next class we'll start with a new chapter. I think we'll go with another, that is coordination compound, or we'll see. If you want, we can go with the organic chapters also, right? So thanks for joining. We'll continue in the next class.